Welcome to the introduction on sustainable materials. In this lecture, we will explore how different building materials and systems impact sustainability, including their energy footprint and historical development. I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. I will guide you through key concepts related to sustainable building materials in this session. We reference key texts such as Materials and the Environment by Michael F. Ashby and Turning Point in Timber Construction by Ulrich Dangel. These books provide foundational insights into eco-informed material choices and the evolving timber economy. This introductory slide distinguishes the key building systems and the material categories used in construction. It outlines 5 fundamental building systems: the site system, structure, enclosures, services, and interior system. Under each building system, there are materials and subsystems that serve specific functions within that system category. The diagram provides a framework for thinking about how a building is put together, the major systems that make up a building, the various material types from which those systems can be constructed, and finally, how these choices ultimately influence the building's overall environmental performance. The site system includes the building's site infrastructure, landscape elements, pathways, and any outdoor or urban furniture on the site. The site system provides the infrastructure necessary to operate buildings such as energy, water, sewer, and IT services, as well as protection from climatic disasters such as storms, heat waves, flooding, and so on. The building structure refers to the building's skeleton, such as columns, beams, and load-bearing walls. The chart shows how material choice affects embodied energy and environmental footprint. Structural elements carry the highest loads and often have significant embodied energy. A steel structure is shown to require roughly 1.2 gigajoule per square meter, a concrete structure about 0.9 gigajoule per square meter, and a wood structure around 0.67 gigajoule per square meter. This comparison highlights that wood construction tends to have lower embodied energy than concrete or steel. Enclosures protect the interior from the environment. They are elements like walls, roofs, and windows, and are essentially the building's envelope. Enclosure building materials under the enclosure system are categorized into 4 broad families. Metals are one category. For example, aluminum, steel, copper, and bronze are listed as common metals in construction. Next, ceramics are shown, a category that includes materials like brick, terracotta, glass, and even concrete. The polymer group includes acrylic plastic, PMA, polycarbonate, and composite materials such as GFRP, glass fiber reinforced polymer. Natural materials are renewable or bio-based materials including bamboo, hardwood, softwood, and even materials from agricultural waste. Building enclosures are a primary contributor to aesthetics, building performance, and sustainability. Building service systems allow a building to operate as an integrated functioning whole. They include HVAC, heating, cooling, and ventilation, electrical systems, IT network, lighting systems, plumbing, life safety systems such as fire alarms and sprinklers, transportation systems such as elevators, and other utilities. These systems ensure health and well-being for all occupants. Interior systems include finishes, furnishing, and appliance, which complete the building's final system. The interior system's textures, colors, materials, and details impact the user's comfort, perception, and productivity. This slide presents a breakdown of how embodied energy is distributed across the different building systems. In other words, it illustrates which building systems account for what portion of the total embodied energy used in an office building. Embodied energy is the total energy consumed from cradle to gate. In construction, it includes energy associated with raw material extraction, material fabrication and manufacturing, transportation, and related processes. The building enclosures contribute the most to embodied energy, followed by building service systems and structural systems. Embodied energy is determined by the product of the total mass, tons, of building materials and the corresponding embodied energy value for each material. For example, if the building is a high-rise, which requires massive concrete foundations and structural framing, the structural system will likely dominate the embodied energy footprint among other building systems. This is because they account for a large volume and mass in the building, and steel and concrete have a relatively significant amount of embodied energy. Each of these systems, from the foundation and frame to the finishes, carries an energy cost to create and install. The chart on the slide visually emphasizes the importance of material selection for each building system. Shown here is a timeline of major material ages in human history, highlighting how the dominance of certain materials has defined each era. The chart indicates relative importance on the vertical axis, suggesting how dominant each material family was at a given time. As time progresses with the horizontal axis, each new material innovation rises. The overall story is that human civilization has continually progressed by adopting new materials, from naturally occurring materials to metals, plastics, and molecular engineering in the contemporary era. Each age doesn't mean the old materials vanish. We still use stone, iron, and so on. But it shows that the driving force of technology and industry has shifted from one material to the next as our society has advanced. This slide provides a big picture look at the global production of materials and our world energy consumption. On the vertical axis, it shows the annual world production of major material categories measured in tons per year. One striking point is the sheer scale of fossil fuels like coal and oil extracted by mass. Following fuels, construction materials such as steel and concrete constitute another significant category given their extensive global use. We mine and refine massive quantities of metals, iron, aluminum, copper, etc. each year, though the total weight is less than that of fossil fuel extraction. We also see polymers, plastics, and ceramics, cement, concrete, brick, glass, etc. as substantial categories, and others categories noted as well, which includes all remaining materials not in the main groups. For example, wood and other biomass used as material might fall here. The chart's takeaway is the staggering volume of materials society consumes annually, on the order of billions of tons, with fuels and construction materials dominating global resource flow. The other side of the slide addresses world energy consumption by source. It breaks down global energy use into 4 source categories: fossil fuels, nuclear, solar, and lunar. The vast amount of energy comes from non-renewable sources such as coal, oil, and natural gas. Only a much smaller fraction is supplied by solar sources, which here includes renewable energy ultimately driven by the sun, such as solar power, wind, and hydropower. An even smaller energy production comes from lunar sources such as tidal energy, driven by the moon's gravity. This chart highlights how heavily our world currently relies on fossil energy, and by the same token, how much opportunity there is to grow the contribution of cleaner energy sources in the future. Summary highlights 1. Key 5 building systems include site, structure, enclosures, services, interiors, and each having distinct materials and environmental implications. 2. Wood materials are a sustainable alternative to traditional building materials with lower environmental impacts, while steel and concrete are more energy intensive. 3. The exploitation of fossil fuels and the manufacturing of steel and concrete intensify global material consumption and pollutant emissions. 4. Global energy supplies heavily rely on fossil fuels, while the contribution of renewable energy sources such as solar, wind, and hydro remains modest. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We appreciate your interest in sustainable materials and their role in architecture.